Hello, we learn about AirWEdge today. It's an experiment where we form interference fringes. So we'll see the small derivation. Why it is called AirWEdge? We'll start with why it is called AirWEdge. We'll see a small derivation and we'll see how the experiment is being done as well. Okay, so let us go into the AirWEdge explanation. So let's start off. Let's first see why it is called as AirWEdge. Okay, so in your lab you would have seen two thin glass plates which would have been used in your AirWEdge experiment. These are the two thin glass plates, and this is how it appears to your eye. Actually, in between these two glass plates, you will have a very thin material. It may be a piece of wire, it may be a piece of hair, or it may be a piece of paper, or it may be a piece of blade, or anything thin is fine. So you keep a very thin material. So this is actually a magnified image what I am showing, including the angle. You get the two glass plates inclined with respect to each other. This is what you end up with. You end up with this. So you have this material in between here, right? So now you have these two glass plates inclined at an angle to each other, and you see a V shape here, which could also be called as a wedge shape. This V shape is also called as a wedge shape, and in between these two glass plates, what is trapped is air, hence the name AirWEdge. Right? This is a wedge shape, and what is trapped inside is air. So what happens is reflections from these two plates give an interference pattern. So this is what we'll be seeing. First, let us see the small derivation, then we'll see how the interference fringes are being formed. Okay, so we'll start from probably even the interference fringes. You'll have two glass plates. One here. I've just drawn a rough sketch. So light which is incident on these two glass plates will be reflected from the bottom plate. It will also be reflected from the top plate. So these two beams of light act as two different sources, and when they enter the eyepiece, undergo interference, and you will get interference fringes. You will get interference fringes, and you will be analyzing the bandwidth of which is the distance between any two fringes. So let us just see the derivation for AirWEdge first. Okay, let us see the derivation for AirWEdge. So you have these two glass plates here. You have these two glass plates here from the origin. So I am assuming the nth fringes here, and I will also take the n plus 1th fringes here. And the distance between these two is beta. I'll explain this. And the angle between the two glass plates I am assuming is theta. So what do I mean by this? So I have interference fringes, right? I have interference fringes. Suppose I take this as the nth fringe. I could take this as the n plus 1th fringe. And the distance between these two, actually they will be equally spaced. I have given this for your understanding. The distance between these two fringes defines the bandwidth. So I have this nth fringe at a distance L from the origin, and I have the n plus 1th fringe at a distance beta from the nth fringe, which means from the origin the distance of the n plus 1th fringe is L plus beta. Let us keep that in mind. So now let me start with the equation 2 mu t cos r, 2 mu t cos r is equal to n lambda. You know mu is a refractive index, and the refractive index of air is 1, so you will have mu is equal to 1. Let us go into cos r, which is the angle of refraction. So if you go into cos r, which is the angle of refraction, the angle of incidence is extremely small, which means the angle of refraction is almost equal to 0. So you will have cos r is equal to 1, because cos of 0 is 1. So you could modify this equation to give 2t is equal to n lambda. Let us give this an equation number. We'll call this some equation 1. Now let us take this triangle. I need the ratio between this and this. So if you take this as a triangle, you know this is the opposite side and this is the adjacent side. So you could write tan theta is equal to, I'm sorry, this is t, this thickness, this breadth is t. So I could say tan theta is equal to the opposite side t divided by the adjacent side L. But this theta is extremely small. You know, the two glass plates actually look like one. So you could say tan theta is almost equal to theta. So I could write theta is equal to T by L. Okay, theta is equal to T by L, or I could say T is equal to L theta. This is equation 2. Now you could now substitute 2 in 1. You could substitute 2 in 1. So what will you get if you substitute 2 in 1? 2 L theta is equal to n lambda. This could be my equation 3. This is for the nth fringe. What can I write for the n plus 1th fringe? I could write 2. Instead of L, I will be writing L plus beta, because that is the distance of the n plus 1th fringe. Theta is equal to, I am talking about the n plus 1th fringe, n plus 1 into lambda. So if I need the fringe width, I will find the difference between equation 4 and equation 3. So I will write 2 L beta into theta minus 2 L theta is equal to n plus 1 into lambda minus n lambda. So when I subtract the left hand side and subsequently the right hand side, I will be ending up with 2 beta theta is equal to lambda. So now I could bring back the relation theta is equal to T by L. So I can write 2 beta T by L is equal to lambda. So T is equal to L lambda by 2 beta. This will give you, this T is equal to L lambda by 2 beta meters will give you the thickness of the material inserted between the two plates. So what would you actually do? So let me write the equation here. T is equal to L lambda by 2 beta meters. What is L here? L is the distance between the point of contact. You could probably tie a thread or a rubber band or whatever to this. This would be L. What is lambda? Lambda is the wavelength of the source, okay, which would be given to you. Lambda is the wavelength. And what is beta? Beta is the fringe width we are going to find out from this experiment. So as I told you, interference takes place. You will find bright and dark fringes and you will find the fringe width. This would be T. This would be T, and you will find the thickness of a very thin material using AirWEdge. This is what you will be expected to reproduce in the exam as well. So the next lecture we will discuss about Michelson's interferometer.